Assalamualaikum. Okay, I would like to present our project about mechanical design and analysis for a post mounting bracket. We have 7 objectives, and I would like to talk about our main objective. First, we want to investigate to design a new geometrical configuration for a mounting bracket and that will effectively support in a post and open environment. Second, to evaluate factors such as strength and heat resistance to determine the most suitable material for the project. Then to deliver a well-designed mounting bracket that meets the criteria: load bearing, capacity, weight, optimization, safety, FOS, and deformation limitation. In this project, the main goals revolves around designing a mounting bracket to support posts in an open environment. To ensure the bracket performance and efficiency, a linear static will be conducted. We have 3 static analysis: linear static analysis, thermal stress analysis, and the third, free vibration analysis. In a thermal stress analysis, in this analysis, we evaluate the structure the bracket will be subject to a temperature increment. And in a free vibration analysis, this analysis will be identify the first 5 structural frequencies in their corresponding mode shape.
The project had given to us, I have done my part, which is linear static. And I would like to explain the method that I do by myself. Okay, the first is list down the properties of the material, and then for linear static analysis, the use static structure, and then import the part of the geometry. We set the material with 7200 megapascal, that is Young modulus, for the Poisson ratio 0.33. Then set material to the part body in model, and then generate mesh with 3.0 mm. Set the boundary condition, fix out the surface part of the surface, and then set the load given 300 Newton and its direction. Later on, set the parameter, choose 1 minus n total of the deformation, and then we can get the result by solution 8, we can get the results of the analysis. And then for the FOS yield strengths, we divided weight maximum once minus, which is we get from the result, which is 500 megapascal divided by 38.331, we get a 13.78174. The discussion, we have considered about these 2 factors important for a specific of cycle loads, which are the final design as a mass of 0.28 kilogram and a factor of safety FOS of 13.174. As I'm said, we have divided, then only we get this value, and the deflection value is 0.2447 mm. The total deformation measures elastic and plastic deformation in a structure of material. It includes displacement and strain. The maximum deformation of 0.247 mm in the loading area of bracket indicated higher stress and deformation due to various loads.
I would like to present the findings from thermal stress analysis conducted using ANSYS Workbench software. This analysis helps us to understand how structures and components respond to temperature-induced stresses. Let's start with the stress results. When we introduce thermal stress changes, the initial temperature was 24 degrees Celsius and the final temperature was 62 degrees Celsius. We obtained the following results values. The maximum stress was 38.331 MPa. The minimum stress was 0.022058 megapascal and the average stress was 4.4685 megapascal. On the other hand, when there was no thermal changes, the stress values were: maximum stress was 38.331 megapascal, the minimum stress was 0.022069 megapascal, and the average stress was 4.4605 megapascal. We can see that there are slight differences in the minimum and the average stress values between the 2 cases. while their maximum stress remains the same. Now let's move on to the deformation values. With thermal changes, we obtain the following deformation values. The maximum deformation value was 2.447 millimeter and minimum deformation was 0 millimeter. The average deformation was 9661 millimeter. In contrast, without thermal change, the deformations were maximum deformation was 38.331 millimeter and minimum deformation was 0.022069 millimeter, and the average deformation was 4.4605 millimeter. The differences in deformation values are significant. The introduction of temperature changes led to much larger deformation throughout the structure. The thermal stress analysis revealed slight variation in stress distribution and significant difference in deformation between two cases. These findings emphasize the importance of considering temperature effects when analyzing behavior of structures.
Since natural frequency related to the bracket, so I will explain the natural frequency. The natural frequency of the structure was referred to as the frequency at which the structure tended to vibrate when it was subjected to an external force or disturbance. Next, difference between natural frequency and force frequency. Natural frequency refers to the inherent frequency at which a system or structure vibrated when subjected to certain condition, typically without any external excitation or force. For the force frequency, also known as excitation frequency or driving frequency. It because refers to the frequency at which an external force or excitation was applied to a system. Okay. This is some way to improve the natural frequency to a bracket. First, structure integrity, and then dynamic response, quality control and testing. We continue with method free variation. First, we need to select the model analysis system and then input the part of the geometry. Set the material we choose, which is aluminium 70756 with Young modulus 72 MPa, velocity 0.33 and density 2810 kg per millimeter cube. And then set the material to the part body, generate the mesh with thickness 3 mm, set the boundary condition, run the analysis, and then extract the natural frequency and total deformation. Final, we will get the corresponding mode shape 6 result. We continue to free vibration result. Since we got 6 mode, the first mode is we got 610.04 Hz. For the second mode, 677.82 Hz. The third mode, 1848.2 Hz. Next, we got 3162.1 Hz. The fifth mode, we got 3619.3 Hz. The last mode, we get 3669.6 Hz.
In conclusion, through the project, we have focused on three main criteria: material selection, load bearing capacity, and weight optimization. By considering a metallic material as raw material, we have the flexibility to choose the most suitable material based on its strength, durability, and heat resistance. When we compare the average equivalent varnishes, stressed with and without temperature, a small difference was observed. The deformation values show significant disparity with the inclusion of the temperature resulting to a higher average deformation and a maximum deformation value. This finding emphasized to significant impact the temperature change can have on the deformation behavior of the bracket. Moving on the concept field vibration, the understanding of natural frequency play a critical role in design and analysis of structures. Thank you.